Hello everyone. This is a demo video for EE542 lab4 fast reliable file transfer. So in this lab, our group has experimented with two UDP-based implementations of reliable transport. In the first experiment, we used a retransmission mechanism that mimics TCP that uh, we retransmit all packets after a, a packet drop occurs. So this one, the first experiment is for achieve UDP IP transfer for files. Uh, so why we call it, we will call it TCP-like uh, in the after, because uh, we are based on the UDP IP, and there is no congestion control in the mechanism. So theoretically, the throughput of this mechanism will be higher than TCP, which is true in our experiment. However, uh, this one is still not good because uh, we have so many packets, and each packet uh, need to wait like 200 milliseconds in the environment. So this one, it is uh, it has a slightly higher performance than TCP, but not enough to be called excellent because it's after we test it, it's less than 20 Mbps. So we tried a second mechanism that is selective retransmission, where we send the sender's information to the receiver to create a form, and the receiver will create a lost list that contains which packet needs to be retransmitted. So, so yeah, it turns out uh, the second mechanism is better, but the workload for the second mechanism for the selective retransmission is uh, kind of big because uh, there are some bugs in our program, such as the sender sends uh, packets faster than the receiver receives the packets. So it can behave well in transmitting small uh, files, but uh, we made some problem in like transfer in 1 GB file, because when our packets the sender's packets send too fast, the receiver cannot receive the packets for some reasons. So this is our network topology, which is based on the former labs. So in experiment 1, which we call it TCP-like, uh, we call it TL. Uh, in the following. So we test all three cases. The first case is bandwidth 100 Mbps per second, 10 ms delay, and 1% packet drop, while the second case is 200 ms delay and with higher 20% packet drop. In the third case, no packet drop, but the bandwidth is set set to a lower level. So we test these three cases in both MTU of 1500 and 9001. So this is the mechanism for our TL. So the server creates a socket and keep listening for downloading requests from client. While we open client, we are asked to type in the file name we want to download from the server. So when the client sends a request to the server begin to send file, and for each packet, the client will send acknowledgement. So, well, if a packet is dropped and the next packet goes in, there will be a mismatch in client packet ID. So the client will send a retransmit request, and the server will transmit the lost packet again and send all packets after the dropped packet. So this is our result for 6 cases. So let me show you the result. We tested out that uh, it is very like TCP, while with MTU 1500, it's 2 Mbps. It's very low, but it can work somehow better in MTU of 9001, but still in a high latency and this is 20, sorry, this is 20 loss rate environment. It cannot behave well because too many acknowledgements need to be confirmed in that case. So the file transfer is not that good. But in some better cases with lower latency and lower loss rate, the throughput is approaching like 20 Mbps, but it is not able to exceed 20 Mbps on AWS. So let me show you one case that with bandwidth 100 Mbps, 10 ms delay, and 1% packet drop, and with MTU 9001. So I'm gonna show my code first. So this is the code for client. For MTU, we change this buffer size. For MTU 9001, we use 8192, and for MTU 1500, we use like 1024. This is because if we set the buffer size too large, it will exceed the buffer size, and the program will it cannot transfer file if if the buffer is exceeded. So for both cases, we construct packeting for, and this is for received packets from server. So for client, it is kind of simple. It it needs to know the server IP, to know its address, and then the client create a socket and input the file name to the buffer. So yeah, after that it will send the file name to the server, and it will open a file and prepare to write. So when the server's file comes in, client, it will continue to write in that file. So we can see here. But in such a network environment, it will divide it to two cases. The first one is normal case that no packet dropped. So if no packet dropped, that means the packet ID will equal to uh, the packet ID that server comes in. So if it is successful, we send a packet confirmation back, we set a acknowledgement back to say, okay, we we received this packet, and we write to the file. And the second case is if it is a retransmit packet, we need to set the packet ID to the lost packet and send back to server to tell the server to reset the ID to the lost packet. Yeah, and after that we just close the socket and close the file, and we get a whole file. So for server, it is a little bit complicated than the client. So yeah, for server, this is the same structure. So we need two IDs, the send ID and the receive ID in server. And at the beginning of the program, we need to create UDP socket and bind it. And this socket keeps listening for upcoming requests. So if a request comes in, it will copy that name from the buffer, and to find out if the file exists. So if it's not exists, it will say that file is not found. But if if found, it will start the transmission. So this length is for calculating the bytes, that how many bits we send out. So yeah, there are also two cases in server. If no packet drop, the server just sends. and receive the acknowledgement from the client. But if a retransmission request occurs, it the receive ID is is set to the packet the lost packet ID. So you can see this the idea of this program is simple, but uh, we use acknowledgements on UDP to send the to make file transfer with no loss. However, uh, this mechanism requires too many acknowledgements, and it is not uh, it doesn't behave that well in high latency environments because for example, if every packet need to wait for like 200 milliseconds, uh, the throughput in the end is very low. So that's why I want to show you uh, this case, because in in this case it takes like about 1 minute, one or 1 to 1.5 minutes to transfer uh, uh, a 1G file. However, um, however, in other cases, uh, the transferring time is too long, and it is not suitable to show you in this demo video because it needs to transfer like 6 to 7 minutes. So yeah, uh, after we transfer all bits in the file, we just closed it and calculate the time. And also, we need to calculate the throughput and output it. So this is the code. And next I'm gonna show you the yeah, the experiment. Uh, so first we set egress rate limiting on both client and server. And then we set egress rate limiting on BIOS. And then we add uh, latency latency and drop rate on ViOS. Yeah. And we need to move the test file on client. Yeah. And and we need to copy the C file onto the client and server. We compile client TL, and we run server. Yeah, and the socket created and keep listening, and then we run client. So there is a tested file called data.bin. Uh, this is a binary tested file that is randomly caused and its size is 1 GB. So, so we want to download it. And the transmission starts. We can check it here. See if it's, yeah, it's working. So let's wait like 1 minute and to see the result. Yeah, and we can see in this test, file transfer successful. It takes like 90 seconds for 1 Gbps, and the throughput is about 12 Mbps. So we say it performs better than TCP, but it's not that good for UDP transferring. Yeah, and we can see the client here. Now we have a data bin. Can and now we do MD5. They should create a MD5 file for check the data bin. Yeah, and now it has a data bin MD5. So we copy it to client. And to check it, we use MD5. So yeah, and it shows data bin okay, which means we transfer data bin with no loss. So as you see, the throughput between for this TCP-like mechanism is around 10 to 20 Mbps, which is not good enough. So we also tested experiment 2 with several tests. Yeah, and here are some critical thinking from the lab report. You can take a look.
Firstly, we will test the throughput of our FTP program on the situation that MTU equal to 1,500. As you can see here, 1,500, 1,500, and 1,500, 1,500. And let's add the egress rate limiting. Okay, I delete the old rules and add the new egress rule. Also add this rule for server for router. Now let's use hyperv to test the environment, the network speed. Here is the server, here is client. The TCP, the rate of TCP is only 68.2 megabits per second. I'm sorry. Let's test the UDP. As you can see, the speed of the UDP is almost 100. It's 95.3 megabits per second. Now let's add 10 millisecond latency and 1% packet loss rate on both transmitter and receiver. Let's test the throughput using UDP. The throughput is almost 100 megabits per second. It's 95.7, and we also test the throughput use TCP. Throughput is only 15.6. Now let's test throughput from server to client. So as you can see, the throughput is almost 100 bits per second. It's also 95.7. Now we use TCP to test the throughput. It's only 10 megabits, 11.7 megabits per second. It's so slow. And of course, that's ping each other. It's correct. And okay, let's this is server, this is client. So let's generate 1 gigabytes file at client side. 1 gigabytes from the FTP program. And update the server code, and let's run the server again and again. And the server won't print those count numbers. What we should do is wait for the finish transmitting of the file. Okay, now the file has been transmitted, and as you can see, we use the packet size of 1400, and the file has been split into this number of packets. This is the receiver, and let's look at the sender. Sender firstly open the file and check the size of the file and split it into those numbers of packets and send, and the throughput is 26 to 84 megabytes per second. And let's check the integrity of the file, MD5 some. As you can see, these numbers are same. Let's just do another test. During the RTT equal to 200 milliseconds and the job rate equal to 20%. Let's ping each other. As you can see, the latency is almost is around 200. And test the throughput. As you can see, if we use TCP, the throughput is almost 0. And we use UDP. You can see we use iperf -u -h, the SS, and to test the throughput is 77.9. Now let's test the throughput under the situation that we have 20% loss and 200 millisecond latency. Okay, the transmission finished. As we can see, the throughput is 7.14068 megabits per second. And let's check the integrity. So as you can see, the hash code are same. And let's delete the rules right now. Check. And add a new rules on router. Add a grace rate limit on server and client, and limited the link speed of the link to one. No, I'm sorry. And add 100 milliseconds to the link. I'm sorry, I shouldn't add the parent rule in the server. I should add it in the router. I'm sorry. Yes, and I have added the limitation here and the limitation of the link speed here. So I can show you the rules. And the pin each other is correct because the latency should be 200 milliseconds. And test UDP throughput is around 77. It's good. And test TCP throughput. It's only 15, around 20 megabits. Now let's test the throughput of the FTP. So let's reboot this before. And the file transmission finished. And let's test the integrity. I'm sorry. By the way, the throughput is 9.0, and as you can see, the hash code are same, so it's good. And this is the three situation test for the situation MTU equal to 1500. And then I will show you the next three tests measurement under the situation, which is MTU equal to 9001. As you can see now, for Ethernet here, MTU equal to 9001, 9001, 9001. So all of them are 9001. And show the rules and delete the rules. Here I already clean the rules and add the egress rule to test case 1 and case 2. Now we have firstly check the throughput first. As you can see, the throughput is around 100 milliseconds, 100 megabits. So it's good. Also check the TCP. The TCP throughput is around 77 or 75. And for the case 1, we should add 10 millisecond RTT and 1% drop here. So let's transmit the file. So let's remove data bin first. And the file transmit successfully. The throughput is 9.0 megabits per second. And let's check the file integrity. As you can see, it's okay. Now test case 2. So I shouldn't add here. I should add here. Okay. Let's make it again to test case 2. There are 200 millisecond RTT and 20% lost. And the file transmitted successfully. The throughput is 7.11167. Check the show the integrity. And we can find the hash code are same. So now let's test the case 3. Firstly, delete all the rows. Show the rows first. And add the erase rule for router. Now we have 200 millisecond RTT in router, 100 millisecond latency in router, and set the speed limitation for router for server and client. Show the rules. Let's pin each other. Second. It's around 77. It's okay. Then let's transmit the file. We integrity of the file, and we will find the same. So we have finished the 6 tests in two situation, and all of the 6 tests we successfully transmitted the file, and the throughput is between 7 to 10. And yeah, so this is the this is for the 6 tests. Next, I will explain the code. Let's see sender first. Firstly, we assigned the buffer size equal to 1400 because the MTU, one of the MTU is 1500. So I have to set the buffer size smaller than the MPTU because I think it's better. Or if we experience the packet loss, the UDP, if we experience the packet loss, 20%, we will have lower probability to accept the packet if we set the buffer size larger than the MTU. And we transmit each packet for this structure, there are two flags to tell the receiver is this packet is header or not, is this packet is the end or not, and this will tell the receiver the index of the packet, which means where receiver should write the packet to. And here is the data of the packet. Firstly, we open the file, and we read the file size, and we put the file size here. We create a packet and we transmit the file size, file name to receiver, and we create a buffer whose size equal to the file size, which can reduce the times to read the file. We can save time, and we read the 1 GB file into the buffer. Then we close the file. We do this before starting transmit and create socket. Firstly, we send a handshake packet. This packet will send the file info, consists of the size of the file and the name of the file. And we set a timer here. Now we will send here we send 5 times of the file information. We send 5 times to avoid the loss of the handshake packet, and we send the size and the name of the file to the receiver. And here we send the whole file directly. We create a packet here, and we set the buffer of the packet of the data of the packet to 0, and here we calculate the offset. So to let us copy the data from the buffer to this packet and assign the index. So after this, we send the packet. We send this packet. We need to serialize the packet before sending it. And of course, we should set the flag before sending it, because here we already sent the file, so we need to set the header. Is the header to false? Is the end to false? So after sending the whole file at first, the sender will receive a bunch of the lost list, and the receiver will reconstruct the lost list to get a large lost list, then send the lost packet according to the index in the lost list. So here in this big while, there are 2 parts. The first while, this while loop is receiving the lost list, and this while loop. Okay, let's explain this first. In this big while, we have the first while to receive the lost list. Because the lost list consists of a lot of index whose type is int. So I will split the buffer by 4 bytes. So I will get a lot of int, which is the index of the lost packet. And this while loop is just to is also to receive this file is also to receive the lost list. But why we need these 2 while loop to receive lost list? Because the receiver will send an end signal after sending 1 round lost list. So to detect the end signal, we use this while loop. So if we receive the -1, so the sender will know this wrong, the lost list. The sender already received all the lost list. This wrong. If sender received -1, if sender received -2, sender will know the lost list is empty, so there is no lost packet. So the sender will finish transmitting. And here, sender just keep receive the lost list until it detects -1. If it detects -1, it knows there shouldn't be any more lost list. So the sender will send the lost packet. And here just send the lost packet according to the lost list and just read the index from the lost list and calculate the offset using index, multiply the buffer size, and do copy the data in the buffer into packet we created to be sent. Then we sent the data to receiver. And at last, if we already sent all the index in the lost list, the sender will set the flag is end to true, set this flag to true, and send this end signal for 10 times to tell receiver this round packet is finished. So after finish this, we'll go back here again to receive the last list, and send the last packet. And until the sender will do this loop again until it receives the last list. There are index equal to -2, so the sender will know there is no last list, which means the receiver already received all the packet. So after receiving -2, it will set this flag to true, lost list empty equal to true, lost list empty equal to true. So this while loop will be break and go here to finish the whole sending. I'm sorry, it's late night, so it's already 3:32. So I'm so sorry. Let's talk about the receiver. Okay. Firstly, I set the buffer size also equal to 1,400, and I can calculate. And I also set the UDP MTU, the size of UDP packet to 1,400, because it's if the UDP packet consists of several layer 3 packets, if one of the layer 3 packets lost, the UDP packet will not be reconstructed. So the whole UDP packet will be lost. So there is no benefits if we set size of UDP packet larger than layer 3 packets. So I set both of them equal to 1,400. Also create this structure to receive each packet. And as a receiver, it will firstly receive the header, receive the file info, and get the file info, get the size, and use the size divided by the buffer size to get the number of packets, and also calculate the last packet, the size of the last packet. And it can create a file. Firstly, use the size of the file received from the packet info packet, the file info packet, and create a lost list. Because we already have the total number of the packets, we can create a lost list, and we use unordered set to make the search, make a find base, or insert, make all of this faster. So as a receiver, we should do two things. The first thing is receive. The second thing is calculate which packet is received and which one is lost. So we get the new lost list. At last, the receiver will send the lost list to the sender and wait for the new round lost packet. Here is to deal with the redundant handshake and write first packet, because the sender will send a lot of the file info packet at the beginning. So but the receiver only wants receive one file info packet. So I have to use this while loop to receive to receive many times to kill the redundant file info packet, and also receive the first packet and erase if the receiver received the first packet, it will erase the index from the lost set. So as you can see, erase if the set is unordered set, erase is faster. The erase action is faster than vector. And here in this big while loop, we have one small while loop to receive the packet, two while loop to also receive the packet, and here a for loop to send the lost list. Let's explain this. Firstly, the receiver will receive the packet and check if the I guess I explain this first is better. It's better to explain this first. Firstly, if check the lost set, if the lost set equal to is empty, which means all of the packets have been received. So the receiver will break the file the while loop, and if the lost vector is empty, it will send a end signal to sender to tell sender you can have a rest. You don't need to send more packets to me because I already received all the packets. So you can just stop. So after tell the sender, the receiver will just go here to write all the buffer I created before into the file at one time. So there's no need to access the file many times. Let's go back. So if the lost list is not empty, it will just receive, and write the data it received into the buffer I created before. I created a 1 GB buffer to receive the packet data. And while after receive the packet, it will receive the index of it will erase the index of a packet in the lost set. So the lost set will smaller until it goes to 0. So but the sender will also send the end signal after sending all the packet this round. So to deal with the end signal, as you can see, if packet is end equal to true, it will break. So if the receiver received this end signal, it will break because it knows the sender already sent all the packets this round. But also, here is one thing. The sender will send a lot of ending signal, avoid the ending signal packet lost. So I wrote this while loop to deal with the redundant ending signal. If the ending signal equal to true, just continue and receive. And if the next is also ending signal, just continue. So it can kill all the redundant ending signal before receiving the true valuable packet. So if it receives the true packet, it will copy the data of that packet to the buffer and also erase the index of that packet in the lost set and break, because we don't need, because if the receiver receive the true packet, it will goes to this while loop to receive the following true packet. So after receiving all the packet until receive the end signal, it will break, and now to here use the lost set to create a lost vector, because the vector is continuous. So I can just transmit the continuous vector to send the vector to sender. I cannot just send the set because set is not continuous. So I have talked about this. If the lost vector is empty, just send -2, which means the receiver already receives all the packets, and the sender can just stop, finish sending. Also send 3 times to avoid the ending signal, the empty signal lost. But if the vector is not empty, it will split the long lost vector into a lot of small chunks and send those small chunks to the sender. And so if the receiver finished this, it will go back to here to receive a next round lost packet until the lost set is empty. It will go to here. It will receive all the lost packet and write the 1 GB buffer data into the file and close the file. So this is the receiver. And thank you so very much. And in lab 4, our group experienced a lot of problems, and we do our best to solve all of them. For example, we should set, for example, the sender send much quicker than the receive the packet. So there seems a lot of the buffer overflow or something. So we should change the UDP queuing buffer size. We should change the queuing buffer size. We should create a to avoid the buffer overflow. We should also create the 1 gigabit buffer to avoid to access the disk too frequently. Yeah, also we solved the problem that's the UDP data size. We shouldn't let the UDP data size larger than the layer 3 packet size or the UDP packet size, or the UDP packet will not be constructed if one of its layer 3 packets got dropped. And a lot of the big and small problems. Thank you so very much. This is the demo 4 from group 6.